Okay, so we got a couple more requests for problems from section 3-3 in Algebra 2. So let's go ahead and go through them. I'll probably do number 5 and then do number 7 separately. Number 5, you can see it's similar to number 6 in that it has 3 inequalities, though really this one is 2 different inequalities. We'll talk about that in a second. Once we find the vertices of the solution region, we will plug them into the function f and check to see what the minimum and maximum are. I'm going to start off with graphing these inequalities. And like I said a second ago, I think I'll be able to get away with this size here. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 3, 4, 5. 1, 2, 3, 4, 5. Yep, and 1, 2, 3, 4, 5. There. So negative 5, negative 5, 5, and 5, and of course it also goes up to 10. So for this first set of inequalities here, it's y, and at one point it's greater than negative 3, and it's also less than 7. So if I were to have y less than or equal to 7, that would be a horizontal line and shaded below. And the horizontal line would be at 7. So let's go ahead and do that. Horizontal line at 7 and shaded below. And if I had negative 3 is less than or equal to y, what I really have is y is greater than or equal to negative 3. So it's another horizontal line at negative 3. So I go to negative 3, make another horizontal line, and of course I am going to go up. Now, a very nice part about this setup here is if the bounded solution region is in between these two lines, which it looks like it's going to be, um, if it connects on in either of those lines, we already know what the y value is, and it gets really easy to solve the x. But we'll do that in a second. Um, we'll take care of that in a second. Let's graph the other two real quick. Now, this second inequality here, I'm going to divide everything by 4 and I get y is greater than or equal to x minus 2. We'll graph that one in red. And so we start at negative 2, and it goes up 1 over 1, up 1 over 1. Doot, 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 doot. I just counted off really easy in my head so I can get past those green lines and make it really easy. Negative, sorry, y is greater than or equal to x minus 2, which is equation or inequality 2. And we'll do the last one in blue. Same kind of thing. I'm going to subtract 3x. So I've got 6y is less than or equal to negative 3x plus 24. Divide everything by 6. Don't need to flip the sign. Negative 1 half x plus 4. Oh, I forgot to mark the red line is shaded above. So the blue line here is going to be shaded below. It's a y-intercept of 4 and a slope of negative 1 half. So down 1 to the right 2, down 1 to the right 2. Ooh, look at that. That looks like a nice point right there. Bump, bump, bump. I don't need to actually intersect down there. Oh, wait, it's below this line? Okay, so I need this over here. Looks like another nice point there. Now let's go ahead and draw that shape. Okay. So this is equation or inequality 3, and it's shaded below. So that tells me my solution region is between the two green lines, above the red and below the blue. It looks like I have an unbound shaded region here. And look, firstly, I see I've got -6, +7, -1, -3, and my vertex here looks like it's 4, 2. 2. Let's make that a little bit more clear. That is a 2. All right. So it seems like I'm going to have either a minimum or a maximum, and the other minimum or maximum is going to be contradicted by something. So let's go ahead and take a look here and make a table of values for those two coordinates. So I want my f of xy is -12x plus 9y. And I got my xy. And the last column is the f of xy, what the output is. Okay. So I got -6, 7, 4, 2, and -1, -3. All right. See, this whole time I was kind of thinking it was going to end up to be one of these triangular regions in between the lines, and it would be perfectly bounded. But this is an unbounded solution region. It goes forever off to the left. So let's take a look here. -12 times -6 plus 9 times 7. And yep, that's plus 9. I want to make sure I'm not mistyping that there. -12 times -6 plus 9 times 7. I get 135. And I also have, I'll do the bottom one first, -1 times -12 and -3 times 9, that's -15. And now I'll do this top one here, or this middle one here, 4 and 2. Oops. -30. Okay, so already we know 1-3 is not a solution, or it's not a min or a max. We have two candidates, possible max here for 135, a possible minimum here at -30. All we need to do is see if I can contradict one of those things. And the way I do that is I'm going to pick a point. And one thing I like to do here, take a look. I notice I've got the y-axis, or sorry, the x-axis, and it's always going to be a part of the solution region. And it's going to go out to -infinity. So I can take something crazy like -1000 as my x-coordinate and 0 as my y-coordinate. And when I do that and plug it into f of xy, I get -12 times -1000 plus 9 times 0. And what do I get? Well, 12,000 plus 0. So -1000, 0 is going to give me a function output of positive 12,000, which is definitely bigger than this max up here, so it is not a maximum. We should just have a minimum. So I'll say no max, minimum of -30 at 4, 2. And there is my solution to this optimization problem.